Hello, my name is Mark Ditus, and in this video we explore the fermion generations by geometric mean. Please consider viewing the first video of this series titled The Fermions of Generation 1 before you view this one. To begin this video, we have a graphic that shows the geometrically derived square-dimensional square symmetric matrix of fermion mass magnitudes. To compute the geometric mean of all observable fermion GeV squared mass magnitudes, we create a 12 by 12 square symmetric matrix where the main diagonal of the matrix in bold fonts are the actual masses of all fermions after normalization to all positive mass magnitude values, which would be multiplying each fermion GeV squared mass value by 10 million each. And now the electron neutrino is scaled to a 1. The top row and left columns in bold italics are the square roots of the magnitude of each fermion's respective mass as outlined in the first video of this series. All cell values are obtained by multiplying any two fermion vectors, basis vectors from the top row or the first column together, then computing the square root of that product, defined as the geometric mean. Now we view the final version of the geometrically derived fermion mass magnitude matrix. All mass values of the main diagonal, in bold, are actual observable fermion GeV squared masses. The top row and first column could loosely be referred to as the square roots of all fermion GeV squared masses, but to be more specific, they are square roots of the magnitudes of each respective observable fermion GeV squared bare mass. Values from this matrix are at the heart of this video. When letting observable fermion mass magnitudes dictate not only the main diagonal, but the top row and first column vectors as square roots of mass magnitude, we achieve abundant, highly graphic, geometrically sound correlations. We now view a geometric representation of the fermion generations, beginning with a single electron to the left and evolving to representations of all fermions and the top quark to the right. Basically, the overall pattern is the perimeter of any right triangle would equal a leg of the next triangle up. Anyways, to better than 0.9954%, the fermion generations reveal themselves geometrically as right triangles with only basic algebra and Pythagorean geometry. Analysis of fermion mass magnitudes utilizing the first principles of square roots and right triangles evolve into a complete hypothesis. That includes beta decay, atomic structure, and now the fermion generations. The perimeter of the first right triangle shows the down quark and its geometric relationship to the electron, the geometrically derived square root of which is either leg of the down quark right triangle. When we take the perimeter of this triangle, equivalent to the square root of the mass of the down quark, and multiply it by 2, we get results equivalent to a leg of a fermion generation 1 right triangle. This is depicted as the transition from the first right triangle, down quark, labeled, to the second right triangle in the diagram, which is labeled fermion generation 1. This geometric representation of generation 1 is derived from combining two down quark triangles. In other words, perimeters of two down triangles equal either leg of the generation 1 triangle. Geometrically, the electron neutrino plus electron plus up quark equals down quark, all of which add up to 0.00001549 GeV squared, the same value as the generation 1 triangle leg, which is also equivalent to 2 down quarks. Okay. The transition from the generation 1 right triangle representation to the generation 2 right triangle is the most straightforward of all. The perimeter of the generation 1 right triangle is equivalent to the leg of the generation 2 right triangle. The transition from generation 2 to generation 3 follows the same pattern, but includes a multiplication by the mathematical constant E. If we multiply the perimeter of the generation 2 triangle by E, it is equivalent to a leg of the generation 3 triangle. We now view a right triangle that geometrically represents a top quark / all fermion as one entity combination. This is identical to the right triangle at the far right of the former diagram, or the one of all the generations. When defining a leg of a right triangle as the top quark's mass magnitude, we get a hypotenuse that is equivalent to all fermions combined. Also noteworthy is a right triangle with the mass magnitudes of all fermions combined for a leg yields a hypotenuse equivalent to the mass magnitudes of 2 top quarks. This geometric relationship between mass magnitudes of all fermions, treated as one entity, and the mass magnitude of the top quark gives a geometrically feasible definition of top quark confinement. Another way of stating this, the square root of the mass magnitude of the top quark is either right triangle leg times the square root of 2, which is a hypotenuse, is equal to the square root of the mass magnitude of all fermions. We now reveal geometric structure while analyzing matrix columns individually. While all columns exhibit a scalable version of first and last columns, we will explore the first and last columns in detail. The bottom cell of any column has a value equivalent to a leg of a right triangle. Also, the hypotenuse for any right triangle created this way accurately represents the sum of all 12 values for each respective column. First and last columns are in detail as they show identical structure in the sense that both have representations of a top quark for either leg, with the difference being a top quark of the first column is the geometrically derived square root of the top quark, while in the last column the legs are of the top quark represented as the usual GeV squared mass. Calculations are to within 0.9983%. As we end this video, I will ask you my usual question. Why do the fermions exhibit such concise geometric symmetries as derived from first principles? Is it by chance